In simple terms, orbital motion is the motion of an object around a fixed point. It happens when an object is moving forward and has another force acting on it from the fixed point. One of the most common examples used is the orbit of planets around the Sun. Between 1609 and 1619, Johannes Kepler discovered 3 laws of planetary motion, which described the orbits of planets around the Sun. Kepler's first law of planetary motion describes how planets move in elliptical orbits rather than circular, and with the Sun as the focus point. His second law talks about how a planet covers the same area of space in a certain amount of time, in any part of its orbit, meaning that it will be moving faster in point A than in point B in order to cover the same distance, and also because when the planet is closer to the Sun, there is a stronger gravitational pull which causes it to move faster. Kepler's third law describes that the ratio of the squares of the periods of any 2 planets is equal to the ratio of the cubes of their average distance from the Sun. This means that they are proportional and that planet A will be moving faster than planet B due to the smaller radius, and hence stronger gravitational pull, causing it to move faster. Kepler's laws are still accepted up to this day. The most common example of orbital motion are planets rotating around the Sun, which is what Kepler's laws were about, but they also apply to any object in rotation in space, including satellites orbiting around the Earth. Satellites use the initial momentum it gains from being released from the rocket that deployed it to keep it moving forward, which is what is stopping the satellite from falling down to Earth. The closer the satellite is to the Earth, the faster it has to move to stay in orbit due to the stronger gravitational pull from the smaller radius as described in Kepler's third law. Keeping it simply, there are 3 types of satellite orbits. Low Earth orbit, with altitudes typically around 2,000 kilometers or less, medium Earth orbit, with altitudes between 10,000 and 20,000 kilometers, and high Earth orbit, with an altitude of about 36,000 kilometers from the Earth. Tsubame is the closest orbiting satellite around the Earth, being developed by Japan's space agency JAXA as an Earth observation satellite. Tsubame orbited at an altitude of only 167.4 kilometers above the Earth at its closest point in its elliptical orbit, but was decommissioned in 2019. Satellites at these altitudes have to travel at a speed of around 8,000 meters per second, but satellites in high Earth orbit travel at speeds of about 3,000 meters per second, or 11,000 kilometers per hour. All this information has been very useful in real life, but to keep things simpler, in the IB and school examinations, orbital motion is assumed to be a circular motion rather than elliptical. There are 3 formulas for circular motion, as seen here. The omega symbol defines the orientation of the ellipse in the orbital plane. The capital T is the time of an orbital period, meaning the time it takes for an object to do the full circle. The r is the radius, or in these calculations, the distance from the object to the center of the focus point object, and the lowercase m is the mass of the object in motion. Newton's law of gravitational formulas are also used when doing calculations for orbital motion in space, including the rotation of planets and satellites. Here, the capital G is the universal gravitational constant, and the capital M is the mass of the object at the focus point. So for example, when talking about satellites, capital M would be the mass of the Earth, and the lowercase m would be the mass of the satellite. Using these formulas, we can calculate different variables in orbital motion. For example, to calculate the speed of the orbiting object, we can equate the centripetal force to the force of gravity, as the centripetal force is the force of attraction on the orbiting object to the center object. Once we do that, we can simply solve for v, which gives us the square root of gm over r. To find t, we again equate the centripetal force to the force of gravity, but using a different formula in terms of pi, and then solving for t squared, which also proves Kepler's third law. Here is an example question. For this problem, we are using the real-life values in calculating the centripetal force, or the force of gravity, in a problem based on a satellite moving around the Earth. We know the force of gravity is negative g times the mass of the Earth times the mass of the satellite over r squared. For this question, to keep things simpler, we are keeping the mass of the satellite as 1. When we input the gravitational constant, which is 6.67 times 10 to the minus 11, and the real-life values of the mass and radius of the Earth, we get the force of gravity as 9.8 newtons per kilogram, which we know is accurate, and we give our answer in 9.8 milliseconds to the minus 2. For the second practice problem, there is a satellite of mass 10,000 kg circulating 1,000 kilometers from the center of a planet of mass 1.9 times 10 to the 27. First, we start by equating the centripetal force and the force of gravity, which becomes g times m times lowercase m over r squared is equal to lowercase m times v squared over r. For these questions, we shall avoid inputting the values at the beginning in order to keep things simpler. Since there was a lowercase m on both sides of the equation, they cancel each other out, so the mass of the satellite does not matter in this equation. We can also cancel out 1r from each side of the equation, which leaves us with g times m over r is equal to v squared. Solving for v, we get that v equals square root of g times m over r. Now we input the values, and make sure to change 10,000 kilometers to meters for the radius. We get that v equals 6.67 times 10 to the minus 11 times 1.9 times 10 to the 27 divided by 1 times 10 to the 7, which gives us 110,000 meters per second, making sure we put our answer in the correct number of significant figures.